Good evening everybody. So today we will start with the sigma bonding in case of the corresponding theory. What we have started to discuss is the ligand field theory. So the basic proposition what we have seen earlier in case of crystal field theory, where we have chosen the corresponding splitting and the interaction of the metal ion d orbitals, we had, and these metal ion d orbitals are within the crystal field of the different ligands. If they are in octahedral field, we will find that we can have the corresponding splitting of these orbitals, where we have the 5 orbitals in the pre-splitted condition to two sets, one is Eg and that is T2G. But these were our pure d orbitals of the different metal ions which are engaged in bonding with that of our ligand systems. So if we have one central metal ion which is interacting with the 6 ligands in octahedral geometry. So we have a spherically symmetric geometry. So symmetry or the symmetrical arrangement of the different ligands are coming into the picture, and how they are surrounding the corresponding metal ion, that means the symmetry of the placement of the ligand system can show the what type of splitting we can have, whether we have a typical octahedral geometry or the tetrahedral geometry or square planar or square pyramidal geometry. That basically we are getting from the information that what type of crystal field we are imposing due to the presence of these many ligand systems. But this is not everything, because this cannot explain nicely the corresponding position of the ligands in the spectrochemical series, such as carbon monoxide or Cn minus. So to know the corresponding position of these ligands in the spectrochemical series, we have to consider something, that we must have some interaction between metal and ligand. So we should not talk about anything where the pure metal ions are involved only for this sort of arrangement and the placement of the different number of unpaired electrons which are present in the T2G level and the Eg level only. But the symmetry level remains the same, because we are having the same crystal field in octahedral geometry. So if we have some covalency between the interaction of the metal ion and the ligand, so we should have some good overlap between the orbitals that means the orbitals of the metal ion and orbitals of the ligand. As a result, what happens when we consider something, that means we are not talking in terms of the corresponding atomic orbitals, because these d orbital splitting for these system in terms of the crystal field theory is that we are having these pure d orbitals, means these are the corresponding atomic orbitals. So if we just simply consider, instead of having so many atomic orbitals which are only undergoing splitting, and due to that splitting, which is very much similar to the splitting of different energy levels which we see in case of say sodium chloride crystal lattice. If we consider that the molecular orbitals are coming slowly into the picture, so the individual molecular orbitals, if we are talking with some ligand which is polyatomic in nature, so if they are polyatomic, that means individual atomic orbitals are losing their character, and for a polyatomic system we should also have a molecular orbital arrangement that we all know from the simple arrangement of the hydrogen molecule. So, for the hydrogen molecule what we can have, that we know that for hydrogen molecule also we can have the molecular orbitals like this. One is the bonding molecular orbital and another is the anti-bonding molecular orbital. So, the molecular orbital picture for the hydrogen molecule also tells us that these two electrons for the hydrogen molecule is present in a level where we have a bonding molecular orbital. So, if this bonding molecular orbital can be utilized now for some interaction with the metal ion, say if Mn plus is interacting with the H2 molecule, then what we should consider? We should consider the corresponding molecular orbital of the hydrogen molecule and then some combination or some corresponding molecular orbitals on the metal ion. So, this polyatomic system like carbon monoxide as well as Cn minus, we have the typical molecular orbital picture or molecular orbital diagram. These molecular orbital diagrams we must have for the corresponding ligands. First, we must have the corresponding molecular orbital diagram from the ligands, and instead of showing some interaction, that means these molecular orbitals from the ligand side can show some interaction with the corresponding molecular orbitals from the metal side. So, they will interact with the molecular orbitals of the metal ion. So, metal ion should also provide some molecular orbitals instead of the typical atomic orbitals like the P-d orbitals. So, we should have now the corresponding molecular orbitals from the metal side at the same time. So, what happens there therefore, that while talking about the crystal field theory, we have the 3D orbitals. So, now along with these 3D orbitals, we should have the other orbitals, that means the 4s orbital, or in some case we can have also the 3s orbital or 3p orbital or 4p orbital. So, the depending upon the energy of these orbitals and their availability for the system. So, these orbitals can give us the corresponding molecular orbitals from the metal side, from the metal ion side. So, these can have some level for these. At the same time, we should have the corresponding molecular orbitals from the ligand side. Now, these two basically when they interact, we should consider this interaction between the metal and the ligand in terms of the corresponding field, which we will consider is coming from the ligand only. Instead of crystal like lattice, we should have now the ligand field and the treatment for these ligand field part for the metal ligand interaction or some amount of covalency which can be utilized for describing the spectroscopic parameters, the magnetic moment and all other thing will be treated in terms of the corresponding ligand field theory. So, when we consider this ligand field theory and when we are talking about the corresponding molecular orbitals, so we will find that the two different types of interactions we can have when we talk in terms of the simple molecular orbitals for the covalent molecules like carbon monoxide or any other thing, that we can have the head on overlap for sigma bonding and side on overlap for pi bonding. So, we will have both sigma bonding and pi bonding for this. So, the entire spectrochemical series what we can have, we can now explain part by part the presence of these ligands within that particular big spectrochemical series, that what are the ligands which can show good sigma bonding affinity towards the metal center and what are the other ligands which can show some pi bonding affinity which is dominating also to the metal center. So, when we consider the sigma bonding parameter, we must have some head on overlap. So, we should have the corresponding metal ligand overlap which can be considered as an head on overlap. That means, we have the corresponding axis what we considering as the x, y and z axis. So, if it is z, this is x and this is y, and the metal is sitting over at the center of these Cartesian axis. Now, we can have the corresponding ligand. So, if we have some ligand which we earlier we have seen in case of the corresponding crystal field theory, that we have the corresponding dz square orbital, and if this dz square orbital can interact in a head on fashion such that the formation of the CC sigma bond, which we know that how CC sigma bonding can take place due to the head on overlap from the corresponding hybridized orbitals from the first carbon atom to the corresponding hybridized orbital of the second carbon center. So, if we have now just simply we can place the corresponding orbitals, the molecular orbital available from the ligand side. So, if this head on overlap is permissible or can take place, we can have certain amount of head on overlap, and the amount of overlap, that means the magnitude of overlap, that we quantum mechanically we can treat them as the overlap integral, can also tell us about the interaction, that what type of interaction we are having from the ligand which is showing a direct sigma overlap with the metal orbital of dz square symmetry. So, how this L is interacting with the metal ion and what are the orbitals, basically we are talking when in terms of the corresponding sigma bond. That means, we can have when we have the two carbon centers, we all know that corresponding overlap because they are of same type. So, there is no question of having one particular atom serving as a donor atom and another atom serving as an acceptor atom, and this particular situation they are basically sharing these orbitals and electrons are occupying those particular bonding orbitals to give us the corresponding bond between these two carbon centers as a sigma bond. But in this particular situation, when the sigma bonding interaction will take place, we will find that whether this overlap is taking place between the corresponding donation from the ligand to the metal center, or at some time we will find that the ligand can also function as an acceptor or by acceptor species which is accepting the corresponding electron density from the metal side. So, both these two things can happen, and for that particular purpose we should know the corresponding energy level for these sigma bonding interactions. So, what we find that if we have the corresponding theory for the ligand field, what we are getting corresponding to the typical sigma bonding interactions between the corresponding metal orbitals and the ligand orbitals, which are in a particular Cartesian axis, and head-on overlap is taking place between the metal orbital and the ligand orbital, and that also depends on the number of electrons available on the bonding orbitals, which is available from the metal side and which is available from the ligand side. So, in our previous class, what we have seen that from group theoretical notation, if we have the corresponding corrected table for the octahedral symmetry, we can get from all other spectroscopic treatments, we have the corresponding gamma red thing, that means the corresponding reducible representation for the sigma bonding, and this reducible representation can be reduced to three symmetry terms, which is A1G, EG and T1U terms in an octahedral symmetry. So, the point group symmetry, which is OH, can immediately tells us that we have the corresponding molecular orbitals available from the metal side as well as from the ligand side are of these symmetry levels. So, when we have considered in case of only crystal field theory, we have seen that the pure d orbitals, which are not the corresponding molecular orbital, because that was not a molecular orbital treatment, we have the two levels from the metal side as the pure d orbitals which are involved. We have the EG set and the T2G set. Likewise, if you see that when we consider for the ligand field theory for sigma bonding, we are not getting any term from the corrected table as in its irreducible representation of the point group of T2G symmetry. So, that means the T2G level for the orbitals, what we now know very well, that these are the corresponding orbitals which are of symmetry, where the orbitals are pointing towards the intermediate Cartesian axis, that means dxy, dxz and dyz. Those symmetry levels are not coming for the reducible representation for sigma bonding, that means those orbitals will not participate in sigma bonding in ligand field theory. So, only the EG orbitals, that means the dz square and dx square minus y square orbitals will be available for some amount of sigma bonding with the ligand symmetric orbitals. So, the first one what we have seen that what we have the A1G group orbitals. So, is a totally symmetric level for these group orbitals. So, the symmetry group orbitals for the Salk orbitals, the symmetry adapted linear combinations in A1G symmetry can give us the corresponding matching orbitals of the metal side, which is A1G, that means is a typical spherically symmetric one, which is the corresponding 3s or 4s orbital, and from the ligand side also we have the corresponding level, that means if we use 6 ligand orbitals and these 6 ligand orbitals are available for sigma bonding, that means the corresponding symmetry level for the Px, Py and Pz, which is available for overlap with the A1G symmetry of the metal orbital, then we can say that the A1G group orbitals will look like this. So, this is the corresponding pictorial representation of the ligand group orbitals, which is symmetry level, or we can also consider them as the Salk orbitals. Therefore, the corresponding Salk orbitals from the ligand side will have a corresponding pictorial representation like this, and which is available for 100% overlap with the metal orbitals available, and which is typically some kind of head-on overlap, and we will be ending up with some sigma bonding interaction of A1G symmetry. Then the other group of orbitals, which we will find that this is typically the availability of these two orbitals, which we have seen in case of crystal field theory, that dz square and dx square orbitals. What we have seen in CFT, that we have these two levels and the T2G set of orbitals. So, we have the EG and the T2G level. So, we are having so many properties related to something. There we have seen that if the metal ion is a 3d8 system for the bivalent nickel 2 plus, having 6 electrons in the T2G level and 2 electrons which remain unpaired in the EG level. So, these 2 electrons, when they are available, now we find in terms of the corresponding ligand field theory that the corresponding symmetry level is matching for sigma bonding for these EG orbitals. So, these two orbitals only can show some sigma bonding interaction if they are for the nickel 2 plus ion with the corresponding ligand molecular orbitals in terms of the corresponding crystal field theory, and these two orbitals will show only the sigma bonding interaction to the corresponding ligand system. And as a result, what we will find that if there is some kind of this metal ligand interaction and the covalency, that can only be explained in terms of the involvement of the EG orbitals for sigma bonding in these interactions. So, these two orbitals basically, therefore, the dz square and dx square y square orbitals, we know they have the corresponding lobes along the z square axis and a symmetric circular lobe along the x and y axis. So, we have the corresponding electron distribution available along the z axis. So, we have the corresponding ligand symmetry orbital, which will only face from these two as well as these four. So, we have one type of sign for these two level lobes along the z axis and 4 other of different sign from other 4 axis, which are the positive side of the x and negative side of the x and positive y and negative y side. Similarly, for dx square y square only we need these 4 corresponding lobes which are symmetry matched from the ligand side. So, this is typically the corresponding set, that means the EG set of ligand group orbitals which are available, because we have the positive lobe from x axis and the negative lobe from the y axis. So, this is the corresponding matching orbitals, matching symmetry level from the ligand side. So, we have the corresponding EG level or EG group orbitals available for this interaction between the metal and the ligand. So, after A1G we have the EG group of orbitals which are available for this interaction. Next, we have the T1U group orbitals. So, T1U group orbitals which are having symmetry as the p orbitals on the central metal ion. So, now we are talking something which we have not discussed in case of crystal field theory, because we have not considered the corresponding p orbitals for any kind of interaction between the metal and the ligand in crystal field theory. But it is not the true picture or the right picture for explaining the metal ligand interaction, to explain nicely the corresponding amount of interaction between the metal and the ligand, and to explain the entire spectrochemical series we should also utilize the p orbitals. So, these are the corresponding p orbitals along px, py and pz. So, this particular set having a symmetry level of T1U, because which is not symmetric with respect to inversion, and the corresponding matching orbitals from the ligand side which are facing directly towards the corresponding p orbitals. So, this is the only situation only opportunity what we see that the corresponding ligands what is available is giving the corresponding p orbitals for interaction. If it is an oxygen donor or oxygen atom of the water molecule or nitrogen donor from the big ligand system or nitrogen donor from the ammonia molecule, then we all know that this nitrogen and oxygen can provide nicely the corresponding p orbitals for interaction to the metal center. But previously what we were seeing that these electrons present in these p orbitals of the different ligands are providing the corresponding crystal field environment around the metal center, but we are not talking anything in terms of the corresponding overlap of the p orbitals of the ligand to that of the p orbitals of the metal side. So, this is the first time that we are considering that PP interaction can take place during complex formation. So, in terms of the ligand field theory, the corresponding PP interaction is permissible for the strengthening the corresponding metal ligand interaction and providing some energy level for the T1U set, that means the p orbitals on the metal atom or the ion, which can be utilized for interacting with the ligand orbitals to give us a corresponding head-on overlap, and this head-on overlap can provide us the corresponding sigma bonding interaction. So, apart from these d orbital and s orbitals, we have these p orbitals also which are engaged in sigma bonding. So, what we see that in case of s orbital, if we have one s orbital of A1G symmetry, then 2 d orbitals of EG symmetry and 3 p orbitals of T1U symmetry. Therefore, altogether 3 plus 2 plus 1, that means 6 orbitals are available from the metal side for interaction. Similarly, in terms of the corresponding SALC, that means the symmetry adapted linear combination of the different available orbitals on the ligand atom are also 6 in number, that means 6 plus 6, 12 orbitals are involved for the corresponding molecular orbital formation for sigma bonding. Then we see that the other set what we do not utilized for sigma bonding, that means in case of crystal field theory what we have seen the T2G set of orbitals. So, this T2G set of orbitals what we were having, and in that particular case we are having the electrons available from these T2G levels, and these dxy, dxz and dyz orbitals will not have any matching symmetry from the ligand side for sigma bonding. Therefore, these T2G set of orbitals will not show any kind of sigma interaction with that of our ligand group orbitals or ligand SALCs. Therefore, these orbitals will be there, but they basically show something what we will find when we have the typical molecular orbital diagram in terms of this ligand field, that these orbitals will not show any bonding interaction with that of the corresponding available ligand orbitals. So, what we see that since these ligands do not have a grouping with T2G symmetry, that means from the ligand side we are not getting any such T2G symmetric orbital, and the corresponding orbitals from the metal ion side or the metal side when we are having some complexes in zero oxidation states such as nickel tetracarbonyl or chromium hexacarbonyl, that dxy, dxz and dyz, xz and yz, this is xz, orbitals on the metal ion will be non-bonding when sigma bonding is considered. So, when these three xy, xz and yz, this is xz, we will consider them as non-bonding because we do not have the corresponding matching orbitals available from the ligand side. So, we will have only the set, that means the T2G set, what we have seen in case of crystal field theory, we are talking so much about the occupancy of the T2G level, but we see now that unfortunately these three orbitals will remain as a standby, and since we do not have some matching orbitals corresponding to these, we do not have any kind of sigma interaction with these orbitals. So, now we have all these bonding orbitals in our hand. So, we can construct, like constructing the corresponding molecular orbital picture, what we can draw for simple oxygen, simple nitrogen, simple carbon monoxide or simple Cn minus. So, this particular drawing is also similar to that of our drawing in terms of the molecular orbital formation, where the available orbitals, the atomic orbitals which are available from the metal side are the 5d, the 4s and 4p orbitals, because if we consider that some of these lower level s and lower level p orbitals are also involved, but they are all filled and they will not show any kind of interaction with these orbitals. So, in essence what we find that these are the 4s and 4p orbitals which we are having, where the symmetry level is A1G and the T1U, and we have the corresponding symmetry level from the ligand side also. And as a result, this interaction what we are getting over here is the typical interaction where the ligand orbitals are of higher energy, because these are above the corresponding energy from the 3D level, these are 4s and 4p. So, these two are of higher energy, and these two higher energies basically giving rise to some of these atomic orbitals which are of high energy, and when they are interacting with the ligand side of A1G and T1U symmetry, these four orbitals, we are getting corresponding ligand field related molecular orbitals of A1G symmetry and T1U symmetry. Since these two are basically giving a bonding part and the anti-bonding part, so the bonding part will have the energy close to the ligand side. That means the presence of 4s and 4p level will not change the corresponding energy level much from that of our individual atomic orbitals which were present from the ligand side. So, only thing that due to this interaction we have some amount of stabilization, and that stabilization is basically stabilizing these two sets of orbitals as their corresponding bonding molecular orbitals in terms of the corresponding sigma bonding interactions. So, this yellow shaded line for the bonding part of the molecular orbital diagram is coming from these four orbitals from the ligand side, and then we have the available Eg symmetry from the d orbitals, that means the d z square and d x square minus y square, and these two orbitals when interacting with the corresponding Eg symmetry orbitals from the ligand side, they provide Eg bonding level as well as Eg anti-bonding level. So, what we find that whatever we have, that we have the empty level as the Eg level which is anti-bonding in nature, but the Eg symmetric bonding level is lower in energy. That means which is a typical task to understand that whatever we have considered earlier for the crystal field interaction, the crystal field theory providing out the corresponding crystal field splitting, and we have considered so many things in terms of the crystal field stabilization energy and the corresponding stabilization in terms of this type of splitting which is delta octahedron. But here we find that the Eg bonding level is further more stabilized. That means whatever molecular orbital picture we can have in terms of the ligand field theory, that Eg level will have the corresponding strong bonding interactions which are stabilized in this particular level. Only available orbitals of that same symmetry is the antibonding Eg level, that means the Eg star level. So, we have only the acceptor level available, which is the Eg star level or the Eg antibonding level. Similarly, if we go up further, we will have the corresponding antibonding orbital for a 1G symmetry because it is interacting with 4s, and the antibonding orbital of T1U symmetry, that means T1U star, which is of T1U symmetry. So, they are of much higher energy levels. So, what we find that in this particular situation, like getting the corresponding transitions in the spectroscopic parameters, what we have seen in UV visible spectra of simple molecules like carbon monoxide or imine functions, what we have discussed earlier also, that if we have the corresponding ship base formation, that means between an aldehyde and an amine, giving rise to the formation of the imine, that means C double bond N. So, if we have this particular situation and the chromophoric group, because these are most of the cases solid yellow compounds and we can isolate in solid state, and this yellow to orange coloration of these is due to the presence of these corresponding electronic transitions involving one sigma bond, one pi bond, and the electrons which are available on the nitrogen as the n electron. So, we have the sigma electron, we have the n electron, and we have the pi electron. So, when we are talking about the UV visible spectra of these compounds such that any ship base, if we have, and they are yellow to orange, solid powder, and they can be isolated through the synthesis, say in ethanol, and these compounds are also soluble in ethanol. So, if we take an ethanolic solution of these C bases and run the corresponding UV visible spectra, we get some of these bands, some characteristic bands close to the ultraviolet and the visible region, that means less than 400 or 450 nanometer. So, if we have a multiple feature like this for the absorption and these electronic transitions are taking place due to the presence of some levels what we have considered earlier as these 5 distinct levels. So, when we have these sigma bonding interactions for these atomic orbitals of the carbon atom and the nitrogen atom, we have the corresponding sigma bonding level with those electrons which are occupying in the sigma level. Then we have the corresponding pi electrons for little bit weaker interactions between the corresponding pi symmetric orbitals available from carbon side as well as from the nitrogen side, giving rise to corresponding pi level. Then what is available is the corresponding non-bonding electrons, that means the electrons which are not involved in any kind of bonding on the nitrogen atom. Then we have the corresponding, because this is typically non-bonding level, then after that we will have these are as antibonding orbitals. So, we have the corresponding pi antibonding orbital as the pi star and the corresponding sigma antibonding orbital as the sigma star. So, during these electronic transitions, if it has 2 or 3 transitions, so in most of these cases we have 2 to 3 transitions and mostly they are sometimes they are very high intensity transitions, that means the charge transfer transitions what we have discussed earlier in this particular classes. So, what we have seen that we have basically two very intense transitions we can consider. One is pi to pi star transition, another is n to pi star transitions. So, during these irreversible spectroscopic transitions for simple organic molecules, what we see that we can have these two transitions involving two of these, that means these are related to the bond formation between carbon and nitrogen when we are trying to make the corresponding ship base from the aldehydes and the amine, that these are the corresponding bonding molecular orbitals. And we have the corresponding antibonding also. So, these are the corresponding antibonding molecular orbitals. So, the same sort of ordering also we will see during the interaction, only thing that we are now having, instead of carbon nitrogen bond formation, we are having now metal ligand interaction, and sometimes this metal ligand interaction can also be the multiple interaction what we see, that in case of several iron oxo compounds which we get in biological system also, that we can have the iron oxygen. So, we can talk about the corresponding iron oxygen multiple bond or the iron binding in hemoglobin such as in myoglobin also, and also we can have the double bond with vanadium and the double bond with molybdenum also. So, these all basically give us the same sort of interaction what we see in case of this corresponding ship base formation. So, the energy ordering for the sigma, pi, n, pi star and sigma star will also be the same if we go for the corresponding bonding, non-bonding and anti-bonding levels for this molecular orbital picture involving these metal centers. So, in this particular case, this particular part, that means 3 to 5 and 6, these are the 6 bonding orbitals in our hand, and what we have seen that altogether we have 5 1 3, that means 5 6 9 orbitals and 9 plus 6 from the ligand side. So, 15 orbitals we are having for sigma interactions. So, 6 of them are bonding, therefore, the equal number should also be there as anti-bonding. So, this is Eg star, A1G star and T1U star, and 3 will remain as non-bonding. The same sort of ordering what we have seen just now for ship base ordering for the different levels, we will have also the bonding level, we have the non-bonding level and we have the anti-bonding level involving 2 plus 1 plus 3 of 6 orbitals. So, as a result what we see that we can have all sorts of transitions possible from there, but likewise for the ship base molecules, the transition from this n to pi star. So, if we consider that this is the n orbital and this is the corresponding pi star orbital. So, this is the most important area where we have the energy gap is less. So, we have the corresponding transition, corresponding spectroscopic transition we can have, or the electronic transition we expect in the visible or NIR region. So, energy gap between this transition from the T2G to EG level is less, and we expect the corresponding transition would be in the visible or NIR region. And what we have been seeing in case of the corresponding simplified version of this ligand field theory as the corresponding crystal field theory, where we see that this particular crystal field theory is basically giving us some levels where we have the T2G level and we have the EG level, and we have the corresponding transition for this T2G level to the EG level. So, what we see that the corresponding level that the molecular orbitals what we are getting, and the molecular orbital diagram is consistent with also the corresponding crystal field approach, because only this part, this blue shaded region, this blue shaded region is matching with that of our crystal field approach, where we have two energy levels. One we are considering as the T2G level and other as the EG level, and we have the corresponding crystal field splitting parameter of delta octahedron due to the two levels. But here the T2G level, due to this interaction in terms of the corresponding ligand field interaction, they are as the corresponding non-bonding levels. So, the non-bonding levels, electrons from these non-bonding levels which will be available for the anti-bonding EG level or the EG star level for the transition. So, this T2G set is present as the non-bonding and the EG set of orbitals are the anti-bonding. So, our transition is very much similar to that of our N to pi star transition. Also, what we have seen in case of the crystal field theory, and this particular part is still there for the transition in the ligand field diagram also. So, we have the thing that this is the HOMO level, that means the highest occupied molecular orbital, because we are talking in terms of the corresponding energy levels for all these as well as these non-bonding levels. So, the metal ion or the metal atom giving the electrons which are occupying the T2G level will serve the purpose as the corresponding HOMO level or the highest occupied molecular orbital level, which is highest in energy, and the EG is giving the corresponding EG star level, which is the corresponding lowest unoccupied molecular orbital. So, we have the corresponding HOMO-LUMO gap, and we basically, due to this sort of interactions, we basically modify the corresponding HOMO-LUMO gap. And interestingly, what we can see that we do not have any control for the energy level for this EG level. What we have been considering for the corresponding crystal field interactions, that we are talking that since we have the crystal field splitting, we have the stabilization for the T2G level and the stabilization for the EG level because of the head on interaction from the EG orbital, that means the dz square and dx square minus y square orbitals, and they are getting destabilized, and that is why they are of higher energy. But it is not the fact is that the EG level, how the EG level is involved in sigma interaction with the EG level from the ligand side. So, if our energy for this EG level from the ligand side are different, our stabilization energy for the EG level as well as the destabilized level of the EG star will also be of different energy. That means, the metal ligand overlap from the EG orbitals of the ligand side do control this particular energy gap. It is not the entire crystal field which will be responsible for giving us the corresponding crystal field, and we are talking in terms of some interaction from the ligands which are giving our strong interaction. We will have bigger splitting. If we have the metal ion in the +3 or +4 oxidation state, we will have bigger interaction, but in most of the cases what we will find that the stabilization of this EG level from the ligand side, how it is stabilizing the corresponding bonding level, bonding EG level, will tell us the corresponding gap between this EG and the EG level, T2G level and the EG level. So, what we see that the electrons from the ligands, which we are having the 12 electrons from the 6 ligands. So, ligands are providing altogether 12 electrons, and per electron we are having 2 electrons, because we are considering the ligands as 2 electron donor, whether it is the oxygen atom of the water or nitrogen of the ammonia molecule. So, all 12 electrons will come to occupy these 6 orbitals, and they are all filled. So, due to these interactions, what we are getting, these are filled by the ligand orbitals. So, the ligand orbital, because they are of low energy compared to the metal ions. So, what will happen in the next step, the metal ion orbitals, that means the T2G level will be filled from the metal orbitals. So, the pure metal orbitals they are of only the metal D character are filled in the T2G level, and we are having only the corresponding p orbitals which can be considered as the p star level from the ligand side, or the Eg star level which will be our good acceptor level. So, we just basically level the entire part for this donor and the acceptor level, and we have filled this particular level as the 12 electrons from the ligand side, and the electrons from the 4s and 3d orbitals of the metal side in the first transition row will occupy this middle portion of the diagram. So, basically when we consider that the Eg and T2G level, it is the 3d electrons, not 4s only, there is a 4s also, the 4s is of higher energy. It is the 3d level of electrons which will occupy these levels. That means, if we have for nickel 2 plus, so in truly speaking, when nickel is interacting with ammonia or water molecule, so all the 12 electrons which are coming from the ammonia and the water molecule will fill up these 6 levels, and the nickel electrons which are 8 in number, they will occupy this non-bonding T2G level and the antibonding Eg star level. So, Eg star level will have 2 unpaired electrons. So, the property for this is basically a typical non-bonding level, and this LUMO level will tell us all these properties related to the nickel 2 plus. So, when we have this bonding, antibonding and non-bonding level, and we just simply say that the interaction between the HOMO level and the LUMO level, what we have ignored in case of the crystal field theory, that crystal field theory does not take into account the overlap of the ligand and the metal orbital. So, this is the principal drawback of this particular theory, where we are not talking in terms of the overlap of the ligand and metal, but this is not the true and the most realistic picture in our hand, because we should have the metal and the ligand overlap, and the ligand orbitals, particularly these 6 orbitals from the ligand side which are functioning as a bonding orbital. So, the strength of the metal ligand bonding or the strength of the metal complex or the metal ion complex is purely depending on this sort of interaction, where we have the 6 orbitals of A1G, T1U and Eg symmetry serving as this blue shaded, yellow shaded region as the bonding level. So, this sort of bonding basically now we see in terms of the ligand field theory, that the bonding interaction is basically stabilizing the metal complex, and whatever other spectroscopic, magnetic and other interactions we should have is coming from the non-bonding and anti-bonding interactions. And we have the corresponding non-bonding level as our HOMO level. So, HOMO is our non-bonding level and the LUMO is the anti-bonding level, and these two levels are basically characteristic though for these stabilization in terms of the corresponding number of electrons and their transfer from one level to the other. But the typical thing, that means the bonding for these metal complexes are basically due to the bonding from the ligand orbitals. So, this particular picture, the entire molecular orbital energy level diagram for a typical octahedral complex, can now explain the availability of these orbitals, how they are interacting with the ligand group orbitals which are symmetry level, that is why they are also known as SGOs, the symmetry group orbitals, and how these energy levels are available for these different types of characters and the properties. So, next we can consider in our next class that how we consider the corresponding pi bonding interactions. So, whenever we have these corresponding pi bonding interactions, so if we have the ligand and if we have the ammonia molecule in our hand, and we will find that from this ammonia molecule we will having the 3 orbitals available one is Px, another is Py and another is Pz. So, one we have utilized say Px orbital we have utilized to overlap with the metal ion. So, already we have considered this one particular orbital. So, this Px is gone for sigma bonding. So, next we will consider the corresponding orbitals which will be available as the corresponding Py and the Pz which are not utilized for sigma bonding. So, these two orbitals will give us the corresponding pi bonding in these metal complexes. So, next we will see how this bonding also can support some of these properties of these ligands in these metal complexes. Thank you very much.